Well, I'd like to thank the organizers for inviting me to give the talk, and thank you. Okay. Okay, thank you. Okay, so I'm certainly not Priscilla. You'll notice the difference a little bit later, I hope. So I hope you're not disappointed. I'm going to give you an introduction to topological insulators and then talk a little bit about spin-excitons, which are more like bulk phenomena and how they may interact with the surface. So this is the outline of my talk. It switches back from from surface, bulk. I'm going to give a model for topological insulators, which is based on the work of Semenov, etc., which is what I'll be using. Talk a little bit about bulk properties of SmB6, and then the possibility that these are topological Kondo insulators was brought into our attention by Maxim Zero and et al. And then I'll talk a little bit about the surface experiments, etc., etc. A little bit about de Haas-Van oscillations, and then we'll get to the spin-exciton part of the talk. Okay. Oh, sorry about that. Well, so the model that I'm starting out is with the Dirac equation, which we all know. It has spin-orbit coupling, which has helicity, which essentially means the electrons move in the direction of the spins. The important thing about the Dirac equation for our purposes is that the parity of the upper components are just not related. Parity operator for Dirac equation is just not R goes to minus R inversion, but it's also that you have to, that the lower two components have a different parity from the upper components. You need one of these gamma matrices to do that. Mass inversion, if you remember what the dispersion relation E squared equals P squared plus MC squared, mass inversion keeps the dispersion relation invariant. However, what it does, if you go through all this, sorry again about the notation, is it switches the upper and lower components, and that's essentially parity inversion. So mass inversion is related to parity inversion. This was sort of realized early on by Semenov in 1983, Roman Jakiv, and a couple of his collaborators, Eduardo Fredkin. The model that we'll think of is essentially thinking of a finite slab of material surrounded by a vacuum, where of course, the vacuum you can think about as having a mass of the electron, 0.5 MeV, large MeV, and inside the material, you could have a small negative mass, which of course means that you have the opposite parity that you would have in the system. The mass goes automatically to 0 at the surface, and as those authors showed, that so this is the situation. We have a mass which changes sign at the surface, inside and outside. And you can look for solutions in the form of a plane wave parallel to the surface and some function which is exponentially decaying, sorry again about this, as a function of z. So this is essentially the proportional to the mass z over h bar or something like that. So you have this exponentially decaying wave, and you can apply an appropriate boundary conditions, and what that does is eliminate a degree of freedom. It just relates the upper two components to the lower two components, and it tells you that the lower components have their spins rotated by pi. So the situation is that you have inside or outside the material, you have a sort of bulk Dirac-like dispersion relation and these massless surface states. Of course, massless is a consequence of having time reversal invariance. It gives you a massless dispersion relation. If you look at the Hamiltonian, you have to multiply by gamma z, in this case sigma z. you essentially see that the upper components governed by Hamiltonian, the Rashba Hamiltonian, which has spin-orbit coupling due to the broken inversion symmetry at the surface. And the solutions for that, essentially just a cone, a Weyl cone. It's a Weyl cone because you only have one spin state. Dirac cones would have spin up and spin down, but here you have spin momentum locking. So if you look at kx and ky, you see that the direction of the spin has to be perpendicular. You can see it from here, sigma cross p, that's the Hamiltonian. And so you can easily see spin momentum locking for this system. It's topological, again, because for a number of reasons, here 3 reasons. One, if you look at that surface Weyl cone and you look at an adiabatic path around the vertex of the cone in kx, ky space, you find a non-trivial Berry phase. If you do Landau quantization, you introduce a magnetic field. Well, of course, that gaps it because you've the Weyl cone because you've broken time reversal invariance, but essentially you get a harmonic oscillator type wave functions due to spin-orbit coupling. And what you don't see here is that the solutions are essentially harmonic. There's shifted harmonic oscillators for eigenstate n-1 for a spin-up component of the wave function and phi n down spin. The energies are given by square root of magnetic field times n, and the difference from the normal 2D 2D electron gas is that you're missing a factor of a half. Again, that's the Berry phase. It should be seen in de Haas van Alphen oscillations, as pointed out by Onsager, or the phase should be seen in de Haas van Alphen oscillations, as pointed out by Onsager. The other thing is, if you look at the quantum Hall conductance, that is sigma xy, then what you find is that it's quantized in units of n plus a half. Again, it's different from the usual thing because of the topological nature by pi. Topological Berry phase of pi, non-trivial topological phase. Okay, so this is just trying to correct something in the literature. People often talk about Dirac cones in these things. Dirac cones would be twofold degenerate. We have spin momentum locking. So you actually have, this would be more like a Weyl cone. And as you saw from the presentation, you end up with just one equation at each surface. The front surface, it would be something like that. And at the other surface of the crystal, you'd have the other equation. And so these things are essentially non-degenerate. So, well, please use Weyl cones rather than Dirac cones for topological insulators. Okay, so let's now talk about, so that's a simple model of topological insulators, which we'll see a little bit later. I'm introducing some of the experiments on SmB6. These go back to 1969. And what you see here is the resistivity, which shows this sort of insulating behavior. There's this peculiar behavior at low temperatures that these things plateau, and that's always been a problem. Magnetic susceptibility, or at least the inverse magnetic susceptibility, follows a Curie-Weiss law, and then it folds over at low temperatures. There's the little spike here, which may be intrinsic. So better samples, you still see this plateau at low temperatures, and this is the thing that's sort of caught people's attention, with the topological nature. So how do we explain the bulk? Well, the simple model is just hybridized bands. You have a flat F band and a conduction band which hybridize. There are basically two energy scales that you have to worry about here. There's the direct gap, which is the k equals 0 transitions, minimum energy for that. And then there's the indirect gap, which is from the zone boundary to the zone center. If you look at the density of states, you see you can see the indirect gap quite clearly. If you put the chemical potential in the gap, then you have essentially a semiconductor. For these materials, well, Kondo insulators, these gaps are very small, of the order of 20 millielectric millielectron volts for SmB6, and that's attributed to large Coulomb interactions. The gaps are also, unlike germanium, where you have gaps of the order of 0.8 eV, these gaps are very temperature dependent, and that just comes out from a slave boson by applying a slave boson analysis by assuming large U, projecting out double occupation using these bosons, and you find that the hybridization becomes renormalized, and if NF is sort of close to 1, you can get a very small gap. And the other thing is that the position of the F level is renormalized. So let's get back to these surface states, because that's the subject of interest. Are they topological or not? Well, first of all, you have to demonstrate that this plateau is due to the surface contribution. There have been a number of experiments which have shown this, and I'm just showing one, which was due to the Paglioni group, where they essentially took this material and then they changed the thickness, and you can see that this plateau sort of remains invariant. However, the resistance or decreases, or the bulk resistance decreases as you go through. Another piece of information which may suggest that this is two-dimensional is quantum oscillations. Very early on in 2014, Lee et al. Looked at quantum oscillations in these materials. They found them, and they saw that these oscillations had an intensity which varied like 1 over cosine theta, which is sort of indicating that they're actually two-dimensional oscillations. You're just, the oscillations, of course, are measuring the flux, and if you have an inclined flux, that just gives you the 1 over the cosine theta variation. However, there's no reference here. A little bit later, there was a Cambridge group who looked at oscillations, and they found at low frequencies, the oscillations to within, well, my eye at least, and a number of other people's eyes, look very much the same. But if you look at high fields, they're dramatically different. They find peaks in the Fourier transform at very much higher field, and they concluded that these were three-dimensional oscillations. So the question is whether these, raging question is whether these are surface or bulk oscillations. Well, there are two ways of sort of rationalizing that. One is to say that you have, these are bulk oscillations, but because the system has impurities in there, that you could be seeing an effect from quantum oscillations with impurities. This is the sort of work of Xiao and Fu, which appeared in PRL. The evidence that these oscillations may be due to impurities is if you look at the linear T term in the specific heat, the Cambridge group report values of 20 millijoules per mole Kelvin, which sort of would be indicate that it's actually a bulk, that they're bulk density of states. On the other hand, that number varies dramatically from group to group. And if you look at actually isotopically enriched samples, you get down to a value of 1 millijoule per mole per Kelvin squared. So that says whatever it is very sensitive to the purity of the sample. Another thing which the Cambridge group talk about is the large linear T term in the thermal conductivity. Well, they saw that, but there was a Chinese group and also not Lonzerich, Louis Talifer, the last March meeting, presented an analysis of the linear T term in the thermal conductivity and showed that if you have zero field, he doesn't find that. So again, it shows sample dependence. We know from Kondo insulators that very few vacancies can actually fill the gap. So this is a calculation that done in 2001 for taking a typical Kondo insulator with a hybridization gap, and these are concentrations, and you can see that already at 5% you fill the gap, in which case this provides support for the picture of Xiao and Fu that these oscillations could be, in fact, due to impurities. This is because the gap is so narrow, and you have to use a sort of T-matrix approach in it, that for every impurity, every vacancy you have, it's a missing F states, and what you find is a bound state formed on all the nearest neighboring sites. And so it's a really large thing. So you can think about it percolating very much rapidly than a single impurity. So, okay, enough of that. So that's some things that may be going on with bulk impurities. It could also be oscillations in a pure 3D oscillations in a pure band. This was suggested by Nolan Cooper within a model system. But you can reinterpret this in terms of Bragg scattering by gauge centering. If you think about the usual Landau quantization, you have harmonic oscillators and they're centered at a particular K value. Now, if you Bragg scatter, then the probability of, or the proportionality of Bragg scattering is given by the overlap of those two wave functions. And, oops, we're going the wrong direction. And if you take this into account, as it was first done by Falikov and Cohen, well, actually, they didn't do that. Falikov and Cohen just said there was a possibility of going between the two limits, but the work was actually formalized in this sense by Blount and Pipard, and more recently interpreted by us, which says if these overlaps are very, usually of the order of 10 to the minus 3, if you just calculate the efficiency of Bragg scattering, it's a very small field can actually kill the gaps at the zone, or reduce them to the values which are insignificant, the gaps at the brilliant zone boundary in the direction perpendicular to the field. So that's another possibility. So that's still a controversy which is unsettled. Other indications that these materials are topological is that you find an odd number of Fermi surfaces. That's not sufficient in itself. You have to show that they're spin polarized. Well, we have that they're spin momentum locked. Since we have a Rashba Hamiltonian, that's automatically assumed in the model. There is some evidence for spin texture, but there's a problem with this data in the sense that you're doing ARPES and you're looking at so you're looking at angle resolved, photo emission, spin resolved, etc. So this is a sort of cartoon that you have these 3 Dirac points, and there seems to be some spin polarization. The problem with this experiment is that you have the F level just below the Fermi level, which dominates the spectrum. So what they have to do is to look at the spectrum above the Fermi surface, which means you have to divide by the Fermi surface, because ARPES usually just looks at the occupied portion of the density of states. So this is not the smoking gun. Okay, let me just skip that. And now I want to talk a little bit about magnetic spin excitations in the bulk. This material has, since 1992, has been known to have a low energy magnetic excitations. It's very close to a magnetic instability, even though it's a semiconductor. And you can understand this by using the work of Doniak. By using the work of Doniak, who showed that you can have a slave boson exchange process which gives you an RKKY interaction, roughly, which is proportional to the 4th power of hybridization. RKKY is usually proportional to the second power of a local interaction. In our case, it's a Kondo interaction, which through Schrieffer-Wolff would be V squared over some energy level. And okay, so So what Doniak showed was that there's an effective RKKY interaction, perhaps not with oscillations. But if you take that interaction into account, you can then calculate a susceptibility in the RPA approximation. So there's a non-interacting susceptibility, and it's enhanced by a Stoner-like enhancement factor, which is, of course, Q-dependent. Well, what the magnetic exciton is essentially saying that since we have a semiconductor, that inside the semiconducting gap, the imaginary part of this Stoner susceptibility should be 0. But if you're very close to a quantum critical point, you may be able to satisfy that the denominator goes to 0, in which case you would expect a delta function response. Usual magnetic instability would be at omega equals 0, but we're talking about small frequencies. So this would be an excitation below the gap of the spectrum, would have 0 width, basically because there's no channel for this magnetic object to decay into electron-hole pairs, and as I mentioned before, it's a precursor to a magnetic instability. So if you can calculate using that hybridization model that I showed previously, you can calculate the real and the imaginary parts of the susceptibility. The imaginary part of the susceptibility is 0 inside the gap. Of course, the gap depends on what Q values are. You can go for the smallest, if you have the indirect gap corresponds to the smallest gap, and if you increase Q, if you decrease Q, you would go to the direct gap. So this is just the imaginary part of the susceptibility, the real part of the susceptibility. And I've drawn a line here because our criterion for a spin-exciton was, for this magnetic excitation would be 1 minus J times the real part of chi. And you can see that with this particular line, we have a solution inside the gap. And furthermore, so that gives a spin-exciton dispersion relation. It's sort of shown here, starting out at the Brillouin zone boundary with the lowest energy, and as you go through the boundary, it sort of increases slowly. The amplitudes strongly, if you're at low frequencies, you find a large amplitude. If you're further away from the quantum critical point, you have the spin-exciton has a larger energy, and the amplitude is less Q-dependent. So that's what a spin-exciton is. And as I mentioned, that these precursors for an antiferromagnetic quantum critical point, they were seen as by Pavel Alexeyev in 1992, and they were relooked at by Colin Broholm's group in 2015, and they're still there. They're purely magnetic. These excitations are purely magnetic. They're not seen in the optical conductivity, and these are in-gap excitations, and as you can see, the excitation energy is minimum at the zone boundary, so quite in line. So what has this to do with topological insulators? Well, perhaps nothing, but what I want to show here is, of course, that these surface states has this exponential decay into the bulk, which is given by this small gap. And from experiments, from Fermi velocity, from ARPES experiments, you find Fermi velocities given by 300 to 200. So these things can actually extend quite deeply into the bulk of the order of 15 angstroms from experiments by Neupein et al., ARPES. And this has to be compared with the lattice parameter of 4 angstroms. So it's possible that you have some sort of Kondo-like exchange between spins of your 2D surface metal and the spins, fluctuating spins in the bulk. Of course, there's a reduction in the surface to bulk exchange, the effective exchange, and that can give rise to spin flip scattering. And one can then do the calculation for that. And what you find is, because it's a two-dimensional system and because of the sharp nature of the spin-excitons, that the self-energy has this peculiar triangular-like feature. And this is the real part of the self-energy. I'm not going to explain why. It's just a second-order perturbation calculation in emission and absorption of spin excitons, and what you can see then is that there's a logarithmic singularity at the spin exciton frequency in the self-energy. What that does to the density of states is produce this, sorry. Okay, now I'm going the wrong direction. Almost finished, so. Okay. Okay. Oh. So you get this sharp feature here. You get this sharp feature in the spectrum. And of course, which sort of comes from having a roughly flat resonance, which is, you can think about as a flat band in the density of state. So if you think about the density, if you think about the dispersion relation, then you have two features. You started out with a Weyl cone, and this spin exciton gives you a sort of flat band close to the Fermi surface. Now, ARPES, I think most of the ARPES data shows that these are surface states, and they see this V-shaped density of states, and they see the dispersion relationship. But there's also another group of experiments on the same samples taken at the same on the same machine in Berlin. I think 1 cubed, 1 millimeter. Sorry, 1 milli-electron volt resolution, 1 degree angle, or something like that, which all show the same feature with some very narrow band close to the Fermi surface. There's a lot of arguments. Some people say that this is evidence that the system is not insulating at all. But I think this could be due to the existence of a resonance at the Fermi energy. In this case, the topological aspects, the protection of the surface states comes into question because you have a fluctuating magnetic field from these spin excitations. And as I pointed out, that's essentially breaking time reversal invariance. And so you can have things like scattering from K to minus K. So it's no longer protected. So my conclusions are the spin excitons can produce a strong resonance in the surface density of states. Resonance is extremely temperature dependent. I didn't mention that because, but it's temperature dependent basically because you're looking at final states very close to the Fermi energy. It's observable by photo emission and tunneling experiments. And as I said, the surface states are not symmetry protected. If this exists, then the surface states are not symmetry protected from K to minus K scattering. So with that, I'd like to thank you.